I've been sitting in the Pennsylvania State University Library archive for 3 hours, going through extension bulletins and water treatment papers, and I need to tell you what I found. What I found in a 2020 American Chemical Society paper changes everything you think you know about dirty water. 19 seconds. That is the number. 19 seconds to drive dissolved arsenic out of contaminated groundwater in rural California, using nothing more exotic than iron, electricity, and controlled contact time. Not 19 days, not a 5-stage machine. 19 seconds. I kept reading, because numbers like that usually collapse under inspection. This one did not. The paper held, the mechanism held, the history held. Then the trail led backward, from a modern arsenic study to a 1909 American patent using sacrificial iron and aluminum electrodes, and then outward to farms that still trust earth, stone, settling, and mineral contact more than packaged promises. Here's what the evidence shows, and here's why nobody was supposed to find it. If you think every dangerous water problem demands a branded cartridge, a monthly service plan, or a truckload of chemicals, this video is going to break that spell. 2 dissimilar metals, a low-voltage current, and a simple polishing bed can turn foul water into clear water for a fraction of what most families imagine. In one published test, arsenic dropped from 1,464 micrograms per liter to below the World Health Organization limit in half a minute. And yes, this works even if your house was built 50 years ago, you live in a city, you've never done this before, and you don't have land. Stay with me. Because what I found in Lancaster County and in a 1981 Penn State Bulletin uses the same physics the Persians used to move desert water more than 2,000 years ago. Hold that 19-second number in your mind. It sounds impossible because you were trained to picture purification as a chain of branded stages, each one sold separately. First the pre-filter, then the cartridge, then the membrane, then the sanitizer, then the service visit. This method collapses those steps by making the water generate its own coagulant exactly where the contamination sits. That is why the number feels wrong at first. It violates the business model before it violates the chemistry. The science is brutally simple. Water is rarely just water. It carries dissolved metals, suspended clay, organic haze, bacteria, and colloids too small to settle on their own. When you place iron and aluminum in that water and drive current between them, the metal surfaces give up charged ions. Those ions turn into fresh coagulants inside the water itself. They grab arsenic, lead, chromium, nickel, and the fine suspended material ordinary cloth misses. Then hydrogen bubbles lift some waste, and gravity drops the rest. You already understand the analogy. Think about a cast iron skillet pulling heat evenly across its whole surface. Electrocoagulation pulls charge through the whole bucket the same way. The treatment happens inside the water, not from a powder dumped on top. A 2020 study in environmental science and technology from the American Chemical Society tested iron electrocoagulation on arsenic at 1,464 micrograms per liter. The assisted version pushed that water below 10 micrograms per liter in 0.5 minutes. A 2016 Nature study ran aluminum and iron electrodes for only 2 minutes at 200 coulombs per liter and removed arsenic, cadmium, chromium, nickel, and lead from drinking water conditions, with iron doses near 21 milligrams per liter. That is your equivalent performance metric, multiple contaminants removed with roughly 1 low-voltage charge event, versus conventional systems that need separate media, replacement cartridges, or repeated chemical additions. 1 unit of electrical input. Several units of purification work. That gap represents a massive market in chemicals, filters, service visits, and bottled water every year. And that is why you have never heard of this. Fresh metal ions matter because they form in place. They have not been sitting in a warehouse. They are born at the electrode surface, still reactive, still hungry. That is why cloudy water can crash clear so quickly when the spacing is tight and the current is controlled. Keep the plates too far apart and resistance rises. Push water through too fast and the flock shears apart. Slow it down, let charge and time do their work, and the bucket starts behaving like a tiny treatment plant you can understand with your own eyes. And there is another advantage. Electrocoagulation does not ask you to guess the exact contaminant first. A cartridge usually does. One medium for arsenic, another for sulfur, another for lead, another for sediment. This method attacks the charge relationships underneath several of those problems at once, then hands the remaining polishing work to sand, carbon, and settling. That knowledge never disappeared. It was filed away, it was waiting. I saw the living version in Strasburg, Pennsylvania, just before dusk. The air outside was heavy and wet. The room by the pump house was cool enough that my forearms lost the day's heat within minutes. I did not hear a motor cycling. I did not hear a compressor. I heard a slow drip, one settling chamber feeding the next. Eli told me, plain and direct, that his grandfather never trusted fast water. He let roof water rest, then passed through stone, sand, charcoal, and clean metal contact before anyone drank it. He said, if the water has time, it tells you what it wants to drop. 4 generations. No advertising. No service call. That knowledge came with families out of the Palatinate and Alsace, then stayed alive, because nobody in those communities had any reason to abandon what worked. A Penn State Agricultural Extension Service bulletin from 1981, prepared by Edward S. Young Jr. and William E. Sharp, still documents rainwater cistern design, construction, and treatment in Pennsylvania. The record is there. Eli showed me the old layout with no drama at all. Limestone wall, quiet cistern, a screened inlet, a first chamber for heavier grit, a second chamber for calmer water. He tapped the side of the tank and told me the trick was not force, it was sequence. Dirty water slows, weight separates, fine matter gets caught later, not first. That is not a slogan. That is process control spoken in farm language. The deep history runs far older than Pennsylvania. In Iran, the Persian Qanat system moved water through almost horizontal underground tunnels, with vertical shafts opened at regular intervals, letting gravity and cool earth protect the supply across long distances. UNESCO describes those qanats as a living water technology sustained for centuries, and archaeological work places early qanat evidence in the 1st millennium BC. The Romans solved the same problem differently but landed in the same place. They used settling cisterns, storage basins, and gravity movement before distribution, because clear water begins with patience and staged contact. In Korea, ondol builders sent heat under stone floors through smoke passages, proving something even broader. If you want stability, you work with the Earth's temperature and mass, not against it. Every civilization that mastered extreme condition arrived at the same answer independently. The Amish never forgot. They carried it from the Palatinate to Pennsylvania more than 280 years ago and kept building it because it worked, and because they never needed anyone's permission to do what made sense. The Persians did not learn that from a marketing department. The Romans did not read it in a glossy brochure. They figured it out the way all real knowledge gets discovered, by paying attention to what the earth and the water were already doing. Coolth, gravity, mineral contact, residence time. It never changes. The suppression starts in 1909. That was the year J.T. Harries received a United States patent for water treatment by electrolysis with sacrificial aluminum and iron. It threatened a future built on recurring chemical purchases, centralized treatment hardware, and replacement contracts instead of cheap metal plates and local control. The mechanism was quieter than people imagine. It did not need a movie villain, it needed standards. By the post-war period, conventional coagulation language in water practice centered on alum, ferric salts, chlorination, and plant equipment that cities had to keep buying. A 1947 article by C.F. Bonilla, Possibilities of the Electronic Coagulator for Water Treatment, shows the method was known. A later patent background, US 201-0186992A1, openly states electrocoagulation with aluminum and iron had been patented in 1909 and applied to drinking water in the 1940s. Known, published, then set aside. Then came the paper wall. Municipal guidance rewarded systems that could be specified, bid, and resupplied through conventional contracts. Chemicals fit that world perfectly. So did pumps, feeders, tanks, and service agreements. A family bucket with plates did not. A farm cistern with settling stages did not. Once the professional language hardened around centralized treatment, anything local started looking unofficial even when it worked. Nobody told you, not your builder, not your contractor, not the man who sold your town the next upgrade. Look at who benefited. Water and Sewage Works and similar trade publications built attention around plants, procurement, and large municipal projects. The American Water Works Association shaped the professional conversation around standardized treatment practice. Chemical manufacturers and equipment vendors supplied the recurring materials those standards favored. Different roles, same direction. The magazine needed advertisers. The association needed member consensus. The suppliers needed repeat sales. The financial connection was not mystical. It was ordinary. And ordinary money is usually stronger than dramatic truth. If a city can buy a lum forever, why encourage households to understand charge, settling, and plate replacement for themselves? If a homeowner can be convinced that only sealed cartridges count as treatment, why teach them the older physics? That knowledge never disappeared. It was written out of the manual. It was waiting. An entire field of knowledge disappeared from engineering curricula and household practice. Not because it failed, because it wasn't profitable. And the continuation is not ancient history. In 2023, the International Bottled Water Association spent $410,000 on federal lobbying, according to Open Secrets. In that same year, the American Chemistry Council spent $15.8 million lobbying on federal issues, while PFAS regulation fights intensified. When contamination standards tighten, somebody pays. The fight is over who controls the bill and who owns the cure. You can see the same instinct in the courtroom and the legislature. Water utility groups and chemical interests push hard when new contaminant rules threaten old infrastructure or expensive treatment chains. They do not want simpler, distributed resilience becoming normal household behavior. They want dependence to remain technical, licensed, and billable. The American water treatment chemicals market now runs in the billions of dollars every year. Every alternative installed, every gallon treated at home, is chemical volume that never gets sold again. Now, if you already own a house and you're thinking this only applies to people starting fresh or with land, stay with me, because this next part is specifically for you. You don't need to tear up your foundation, rip out your existing system, or buy equipment. You need one thing they already have or can easily get: a yard, a drill, a bottle, a weekend. Here is the practical build. Start with a food-grade 55-gallon barrel or a square tote that holds 40 to 55 gallons. Set 2 flat plates inside the first chamber, one mild steel and one aluminum, each about 4 inches wide and 10 inches tall, spaced 1.5 inches apart. Connect them to a 12-volt DC power supply or a 12-volt battery with an inline 5-amp fuse. Run untreated water into that chamber through 3/4-inch Schedule 40 PVC. Let it enter low and leave high so the bubbles rise and the flock stays behind. From there, send the overflow into a settling barrel for 20 to 30 minutes. Then move it through a polishing column built from a 4-inch PVC tube, 36 inches tall, packed in layers. 4 inches of washed pea gravel, 16 inches of coarse sand, 6 inches of activated carbon, and another 4 inches of gravel on top to calm the flow. If you want the water cooler and biologically quieter, bury that tube or a horizontal branch line 18 to 24 inches below grade where soil temperatures stay steadier. Use HDPE or silicone insulated wire. Use stainless hardware above the water line. Use a simple ball valve so flow stays near 0.25 to 0.5 gallons per minute. That gives the first chamber enough contact time and keeps the sand bed from channeling. For a family test run, you can process 15 to 25 gallons in 40 minutes the first time, then scale up later. If you want more consistency, drill the outlet holes at a fixed height and mark your plate polarity with paint. Reverse polarity every few batches if scale starts forming. Keep the power leads dry. Keep the electrodes parallel. A crooked 1.5-inch gap becomes an uneven electric field, and uneven fields leave dirty corners in the chamber. Mild steel works because it sacrifices cleanly. Aluminum works because it throws active coagulant fast. Copper is not your plate metal here. Copper belongs in wiring, not in the treatment pair. If the source water is full of leaves or roof grit, pre-strain it through muslin cotton or a 200-micron mesh sock before the first chamber. That protects the valve and buys you longer settling runs. If the source is well water with visible rust, let the chamber run a little longer, closer to 6 to 8 minutes of energized contact before overflow. If the source is pond water, keep the polishing column shaded and use a removable lid so insects stay out. The whole point is control. Small, visible, repeatable control. Test strips help. Use them. Check pH before and after a run, and keep notes on source, smell, color, and contact time. If your raw water starts near pH 6.5, you will often see cleaner flock than you get from guessing. If it starts higher, the settling may speed up. This is not busy work. It is how a family system becomes a dependable household tool instead of a weekend experiment that gets forgotten behind the shed after the first hard storm of summer rains and runoff. Costs stay low. The barrel runs $25 to $45. The steel plate runs $7 to $14. The aluminum plate runs $9 to $18. A small DC power supply runs $18 to $32. PVC, valves, and fittings usually land between $36 and $74. Sand, pea gravel, and activated carbon add another $28 to $61. Total build cost sits between $123 and $244 if you already own a drill. One warning matters more than all the others. The settling stage is not optional. Skipping it causes flock carryover, cloudy water, and a sand bed that clogs early. Let the solids drop, then filter. On a 95-degree day, with nasty roof runoff or rusty well water, this setup can turn brown water visually clear in one cycle and sharply reduce metal load before final disinfection. Clean the sand surface once a season. Replace the carbon once a year. Replace the plates every 2 to 4 years, depending on use. And do not confuse clear with finished. If you are making drinking water, finish with a verified disinfection step after filtration, whether that is boiling, properly dosed chlorine, or a validated UV stage. Clear is not the same as sterile. Bright is not the same as safe. The build I am showing you strips load and gives you control. Then you finish the job correctly. That matters because fear is how the modern system traps people. It tells you that unless a device arrives factory sealed, you are helpless. That is the lie. The truth is harder and better. You can understand your own water if you slow down, test it, watch it settle, and build in sequence. Once you see flock form with your own eyes, the spell breaks. Your conventional whole house treatment package costs $2,800 to $7,400 to install, $38 to $112 per month to run and maintain, and lasts 10 to 15 years before major replacement. This costs $123 to $244 total. It lasts 2 to 4 years for plates, and far longer for the housing. Your choice. Everything I've covered across this channel, root cellar cooling, rainwater gravity storage, off-grid summer ventilation, I've put it all in one place. Step by step, season by season, room by room, in the order the families actually use it. Link is in the description. But stay here, because what Eli built in that settling room is the part nobody is talking about yet. If you're the kind of person who believes that real knowledge has been quietly pushed aside to protect someone else's profit, you already know what to do. Hit subscribe, not for me, for what comes next, because this is not a channel. This is a quiet movement of people who have decided they're done being sold what they already own. I want to hear from you. Drop your state, your monthly water bill, the worst contaminant you have battled, or the oldest water trick your family still remembers in the comments. I read every single one. And your answers decide what we cover next, because that is how this works now. One family remembers a cistern, another remembers a root cellar, another remembers a way of cooling milk, cleaning clothes, or saving seed that never made it into a big box aisle. Piece by piece, the missing manual comes back. Next week, I'm going to show you what a 1946 Penn State document reveals about keeping a summer room cold with nothing but moving air, wet fabric, and shaded mass. The technique uses nothing but muslin cotton, lime wash, and a vent path. And the report from the post-war years that proves building science knew about it decades before selling you sealed box comfort. You're not going to want to miss that one.